So let's discuss integration. In this video, we will talk about integrating the indefinite integral and taking a look at the definite integral and the difference between the two. So here we go. Indefinite integrals. If capital F is an antiderivative of f on a particular interval I, then most general antiderivative of the function on this interval is capital F of x plus c, where c is an arbitrary constant. So if you take a look at this example, the integral symbol looks like an elongated s. And what it tells us is to take the antiderivative of this derivative function. Now, how do I know 1 over x is a derivative of an original function? Because of this dx. This dx is crucial when writing out a proper integral. And it tells us that this function is a derivative in terms of x. So not only is it telling us it's a derivative, but it also highlights the variable in which we should be paying attention to as well. Now we know that the derivative of the natural log function is 1 over x, which is why the antiderivative of 1 over x is ln x. Now, when we take the antiderivative and the result is ln x, where it is a function that has restrictions on it, that's why we need to know that the absolute values need to be placed around the x, because the natural log function breaks down below 0, so we need x to be a positive input. Now, this plus c comes from the fact that when we take a derivative of a constant, it just goes to 0. So when we're looking at this derivative here, there's no way to tell whether there was a plus 5 or a plus 280 after the original function, because when you took the derivative of that, it was 0. So we just put this arbitrary constant c in place of, hey, there may have been a constant, we're really not sure. The constant can always be 0, meaning there was no constant, but we need to put that in as a placeholder. Okay, so the indefinite integral finds the antiderivative, and it's a general form because we're not trying to calculate a specific area, we're just defining what the area looks like. So here's a table of some common antiderivatives. So your power rule, you add 1 and divide in order to take the integral. We practiced this in 4.8 with the antiderivatives we were learning. We love the exponential function because the antiderivative of e to the x is e to the x. Yay! The antiderivative of sine, and so if we think about it, when we take the derivative of cosine, we get negative sine. So if we're taking the antiderivative of positive sine, it must have been negative cosine, and so on. Let's try this one example here. Let me get my pen up and running. I could just do this right in the PowerPoint. So if we are taking the integral of 10x to the 4th minus 2 secant squared, so there are some rules about integration such that if you have a separation of terms between an addition or a subtraction, you can split the integral. Same rules that we have for derivatives. If we have a polynomial, we knew that we could take the derivative of each one of the terms separately and then put them back together for the full answer. So here we're going to take the derivative, or excuse me, antiderivative of 10x to the 4th separately from the integral of secant squared x. Now notice that I pulled out the negative 2, and you can do that just like this 10. I can also pull out and put it here in front, removing it from the integral. So any constants that we multiply everything in the integral by can be taken out and placed in front of the integral. So now what I'm going to do to take the antiderivative of x to the 4th is I'm going to add 1 and divide. So I get 10 times 1/5 x to the 5th power minus 2 times the antiderivative of secant squared is tangent. And then at the end, I'm going to put plus c to indicate that there may have been some constant, and I would never know what that is again. unless I was given some sort of initial value or something that could help me find that constant. So 10 times 1/5 is 2. So my final answer comes out to be 2x to the 5th minus 2 tan x plus c. And that's the answer for this problem. Woo, dropped my pen. Let's talk about some applications, which would bring us to the definite integral. So the evaluation theorem says that if f is continuous on an interval a to b, then when taking the derivative, taking the integral of the function f of x from the a to b interval, what we will do is first we'll find the antiderivative, and then we will plug in b to the antiderivative, and separately subtracting from that, plugging in a into the antiderivative. And this is called the definite integral. So we know that the derivative of f of x represents the rate of change of y equals f of x with respect to x. And f of b minus f of a is the change in y when x changes from a to b. Sounds very similar to a slope formula, and it should, because everything is about a rate of change. Note that y could, for instance, increase, then decrease, then increase again, although y might change in both directions. So we can formulate the evaluation theorem in the following words, that if we wanted to apply this integral, we would take the antiderivative and then substitute in b minus substituting in a. The principle can be applied to all the rate of change in the natural and social sciences. Here are a few instances of this idea. If an object moves along a straight line with position function s of t, then the velocity is equal to the derivative of s of t. So if we're looking at the integral from time 1 to time 2 of the velocity function, we will be taking the antiderivative of velocity, which gives us position, and we plug in the 2 times. This will give us the net change of position, also known as displacement, of whatever the substance is, whether it's a particle or a person or whatever. So if you think about me being at home, for example, so let me talk about displacement real quick. So if we are thinking about, here I am, here's home, and I'd like to go to the store. Okay, so this is the store and this is home. So what is the difference between displacement versus total distance? So let's say that I'm on my little bicycle. Here I am. This is my bicycle. Not the best drawer. Okay, so here's my bicycle, and I rode all the way to the store, purchased a candy bar, yay, and then I drove here back, and I am calculating now this point. Now, displacement is not going to consider the fact that I turned around at any point in time. It is just going to say, okay, I want to know like the GPS location. Where are you? Locate this exact placement. So it'll tell you exactly where you are standing. But if you wanted to know what was the total distance that I traveled, this entire length of the green, well, that's a different calculation that we need to consider when applications are involved. If we just want displacement, we integrate straightforward. But if we want total distance, we need to visualize if at any point in time we have negative area. Negative area would be this place where I turned around and started to return back home. If I got all the way back home, my displacement would come out to be 0. What it would tell me is that there is equal amount of positive area as there is negative area, and therefore 0 tells GPS coordination, you're home. Okay, this tells me that all it says is that I am halfway between home and store, but the displacement formula would not tell me that I was on my way back to home. It would just tell me where I was, halfway between the home and store. So between displacement and total area, you can get the whole story. So if I calculated the total area, the total distance rather, then I would see, well, I know it's a mile to the store. So if my total distance is 1.5 miles and my displacement told me I'm halfway between the home and the store, then what I know is that I went to the store, I turned around, I started going back home, and about 1/2 mile away from home. So there's a whole story that can be told by these two different types of calculations that are the same but yet different. So if we wanted to total distance, we would have to find the absolute value of the negative areas or the places where we turned around. So if we look at this figure, area above the x-axis is the positive area. So this would be me going from home to the store. Negative area is me leaving the store and returning back home. Notice that the area under here is not as big as the area up here, which would tell me I haven't actually gotten back home yet because I would have more positive area than negative. And then this says that I didn't reach all the way back home, so I turned around and started walking towards the store again, which is, again, a positive area. So for displacement, to tell me where exactly GPS location, where am I standing, you'd keep all the signs. You would just integrate straightforward. For total distance, we would have to find this x-intercept and this x-intercept, these zeros, and then we would have to separate the function into 3 integrations. We would integrate the positive area straightforward. We would then take the absolute value of the negative area and evaluate from this point to this point. And then we would go back and evaluate from here to here, but just straightforward with no absolute value needed. So a particle moves along a line so that its velocity at time t is given by the following quadratic function, and it's measured in meters per second. Find the displacement of the particle during the time period from 1 to 4. So displacement needs us to just evaluate straightforward. So technically this graph should actually be a part of part B. So let me just move this down real quick. There we go. Okay, so let's first do the displacement of the particle. So we want to know, where is this particle? Okay, so that would be a straight calculation. So let's do that. Hold on, let me get my pen ready. So we have for part A, we have the integral from 1 to 4 of t squared minus t minus 6 dt. Remember, we can take the antiderivative of each of the terms separately. So I would have add 1 and divide to t squared. So we have 1/3 t cubed. Add 1 and divide to negative t. So we have minus t squared over 2. And add 1 and divide for negative 6, which gives us negative 6t. And this needs to be evaluated from 1 to 4. So that means substitute 4 into this equation and then subtract substituting 1 in. So we get 1/3 4 cubed minus 1/2 4 squared minus 6 times 4. Oh, that's a big parenthesis. Minus the same thing, but with 1 entered in for every t. This will give us the displacement. So here I am, I'm in my calculator, and I have 1/3 times 4 raised to the 3rd power minus 1/2 times 4 squared, so we have times 16, minus 4 times 6, which is 24. Then we are going to subtract 1/3 times 1, 1 to the third power is 1, minus 0.5 times 1 squared, which is just 1, minus 6. So if I put this in my calculator correctly, this gives me a displacement comes out to negative 4.5. So what does that mean in terms of, let's say we were traveling to the store, but here, because this is negative, means that we started away from our store. So I was traveling back home, I turn around towards the store, negative 4.5 tells me that I have spent more time there's more area under the curve than there is above the curve. And we can see that in this drawing. This is the parabola function from 1 to 4, and you can see that the area under is bigger than the area above, making sense why the displacement comes out to be negative. It just means we're more on the negative side than the positive side. Now for total distance, the difference for total distance is we do need to find out what is this point at which the negative area turns into positive area, and we have to split the integral as such. So if we look at this graph, it seems pretty clear that it's split at 2. So from, actually, no, just kidding, 3. So from 1 to 3, we're in the negative, and from 3 to 4, we're in the positive. So in order to calculate the absolute value of the integral from 1 to 4 of t squared minus t minus 6 dt, we need to split it up to calculate the integral from 1 to 3 absolute value of t squared minus t minus 6 dt, and add to that the little piece from 3 to 4 of the same thing. This is not supposed to be an f, this is supposed to be a t. So notice that we'll put the first part in absolute values, as we know that, and we can put the absolute values on the outside. Oh, that one can stay. Bloop, bloop. So we know we need the absolute value of the first calculation. Oops, just kidding. It needs to come out here. Boom, there we go. Because it's area under the curve, so we need to know what the positive total of that is and add it to the area we already know is above the curve. So we already know what this antiderivative comes out to be. Okay, so we do know that the integral of t squared minus t minus 6 dt we calculated to be 1/3 t cubed minus 1/2 t squared minus 6t. We don't need the plus c because we have specific parameters, so the plus c is only given if we do not have upper and lower limits on the integral itself. So we need to evaluate this now in absolute values from 1 to 3, and then without absolute values from 3 to 4. So let's do the absolute value, and we're going to put in 3 first. So the absolute value of 3 cubed divided by 3 minus 3 squared divided by 2 minus 6 times 3 minus, and let's substitute in 1, so 1 cubed divided by 3 minus 1 squared divided by 2 minus 6 times 1. So that's the absolute value part, and we're going to add to that the regular part from 3 to 4. So we're going to do 4 minus 3. So we have 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus, evaluate out 3. So we have 3 cubed over 3 minus 3 squared over 2 minus 6 times 2. So if we calculate those pieces, we will get the total distance. So, all right, let's do the absolute value one first. So I have 3 cubed divided by 3 minus 3 squared divided by 2 minus 18. Okay, then subtract in parentheses 1 divided by 3 minus 1 divided by 2 minus 6. And that comes out to be negative 7.33, but we will want to take the absolute value of negative 7.33. Okay, so that's the first part. That's this part here. Okay, and then we're adding to that what we get out of the second part. So the second part, I'm going to enter my calculator now. So we have 4 cubed divided by 3 minus 4 squared divided by 2 minus 24. Then we're subtracting in parentheses 3 cubed divided by 3 minus 3 squared divided by 2 minus 12. So the second part gives us negative 3.1667. So now we're going to take positive 7.33 because we took the absolute value of the negative version and add to that negative 3.1667. It shouldn't be negative though. That second one shouldn't be negative because according to our graph, from 3 to 4 should be positive area. So let me make sure I did this right. So let me try this again. 4 cubed divided by 3, and this is where I love having in-person class because usually one of you guys would have caught what went wrong here. Minus 8 minus 24. And subtract that 21 divided by 3 minus 9 divided by 2 minus. Oh, I know where I made my mistake. See, this is where you guys would have caught it. I put a 2 here, and this should be a 3. So I put minus 12, and I really should have had minus 18. Oh, that does make a difference. Okay, goodness. I was going to say, then that really defeats the purpose of doing absolute value if it could just come out to be negative. So the second part comes out to be positive 2.8333. So now we take the absolute value of 7.33, which is positive 7.33, and add to it 2.833. And we get a total distance of 10.1633. Okay, so that's the total area if we were trying to find the area without considering area under the curve or under the x-axis versus over the x-axis. So in general, area above the x-axis is positive, area below is negative unless you apply an absolute value. So if f is the function whose graph is shown in this figure, and g of x is equal to the antiderivative of that function, find the following values. Find g at 0, g at 1, and so on. So if we take the function g at 0, notice that if I go back a slide, it's labeled 0 to x. So whatever we're plugging in for x finishes off this integral, the upper limit. So if we're taking the integral from 0 to 0, it means we haven't moved. So there's no area between 0 and 0. We're still in the same spot, which makes sense why the area would be 0. We take the integral from 0 to 1, then what we're doing is we're looking at 0 to 1. It's a triangle. So we would calculate the area by using a triangle formula. So that's 1/2 base times height. The base is a unit 1. The height is 2 units. So 1/2, 1 times 2 gives us 1. To find g of 2, we do the same process. We're finding it from 0 to 2. So we look at the graph. And if you're looking back at the original graph, this is where these pieces come from. So they're just shading from 0 to 2. So this little 2 blocks in triangle. Now we've already calculated the area of the triangle to be 1, so we really just need to calculate the area of this rectangle, which is length times width. So you have 1 times 2, which gives us 2. Add that to the area of the triangle, which is 1, and we get an area of 3. The same process is done for 2 to 3 and 3 to 4 because we can use the areas we've calculated prior to that. We already know the area from 0 to 2, so we just start tacking on the new piece. So notice how we're splitting up this area. We found 0 to 1, we added it to 1 to 2, and now we're adding it to 2 to 3. From 3 to 4, that's negative area, so it depends on whether we want total distance or displacement and whether we'd use absolute values around it. And from 4 to 5, same concept. Okay, and this is our lesson on definite and indefinite integrals.